We have with us Aadityan Ganesh. He's a third-year PhD student in Princeton's CS department, and he's going to talk to us about transaction fee mechanisms. Let's give it up.
All right. Thank you very much for having me, Aviv. Thanks a lot for hosting me. I'm really excited to give this talk here. Okay, let's get started. So, with this, in this joint work with Clay, who was at Yale until like quite recently, and with Matt, we characterize off-chain influence-proof transaction fee mechanisms. So, I'll begin with a quick what to expect. Right. So we'll be looking at transaction fee mechanisms, as the title suggests. And at a high level, TFMs are basically the way through which miners can monetize space on their block, from users who want to push transactions onto this block, right? So technically, the space on the block belongs to the miner, and the miner is not going to do block building out of charity. So transaction fee mechanisms is exactly how the miner gets compensated for letting users send their transactions into the block. So the prior lens before our paper on transaction fees is the following. So it says, look, this is an auction. We know how to do auction theory. And the on-chain equilibrium of this auction is going to be something. And this equilibrium should satisfy three really nice desiderata. The first being it should be insider compatible for the users. It should follow some notion of credibility, and it should satisfy some notion of collusion resistance. I'll get into the details of what these three properties are as the talk goes. And or more specifically, right, like the previous lens said, we have to really make sure that users bid truthfully. We have to really make sure that life is really simple. We have to micromanage all outcomes that happen on chain. Um, the the pitch that I'm going to give in this talk is that maybe that is a little too ambitious for transaction fee mechanisms. But for that matter, like TFMs is not supposed to even dictate all possible aspects of the on-chain outcomes. Rather, I will pitch this alternate lens. I would say like the job of the transaction fee mechanism is to set some loose set of restrictions on what the users and the miner can do, right? Specifically, we will say, okay, if you want to realize this allocation on chain, this is the burn that you have to make in order to realize this allocation. And as long as you are bound by this allocation, comma burn constraints that I set on you, you just feel free to do whatever you want. And specifically, the alternate lens that I pitched did not mention payments at all. And the pitch that I'm going to make is that, sure, maybe just letting users and miner figure out the payments between themselves is not the worst thing to do. So that is going to be the alternate pitch that I'm going to give in this talk. And the end goal of this talk is going to be to characterize for a given transaction fee mechanism what is the off-chain equilibrium it will end up inducing. All right. Before I proceed, if you have questions, like just feel free to ask it out in the talk. In the talk. I don't think we should wait till the end of the talk for a separate question session. All right. So this talk is going to comprise of like two parts. The first half or the first 20-ish minutes is going to be on this alternate lens. So it's going to be more a conceptual part of the talk. And then the next 40 minutes, we'll do some fun math to characterize this off-chain deviations that I mentioned in the last slide. So we'll begin with an example here. We'll start with EIP 1559, and we'll see what it means for EIP 1559 or what it means for people to deviate off chain on EIP 1559, right? So EIP 1559, as all of you must know, it's Ethereum's transaction fee mechanism. So I'll go through all the steps involved in one implementation of EIP 1559, right? So the first is there is some price fee that is announced to all the users. Specifically, this price fee, or it's called the base fee, it is the miner does not have the capacity to set this price fee. It is determined from the history of the previous blocks, depending on how full the blocks were and so on. And once this price is posted, users send their transactions over to the miner, and the miner then routes this transaction to the transaction fee mechanism. Um, Importantly, note that the users do not touch the blockchain directly. The only way through which users can touch the blockchain is via the miner. And the miner, if it wants, it can throw in fake bids, it can censor bids, it can do all kinds of nasty things. But we'll get to those parts later. It's just that the only way for users to go to the transaction mechanism is through the miner. That's the key thing to remember. All right. So now that the blockchain has received bids from the users, it says, okay, for given these bids, this is the probability with which each of these bids are going to be allocated. So what is the probability with which user one is going to be allocated, user two is going to be allocated, and so on. And what are the payments that I got to charge to each of these bids, right? So in AP 5059's case, all users who bid above the base fee P are allocated, and all of them are charged P. So it's literally like, going to a grocery store and then buying a pack of biscuits. If the biscuits has $5 written on it, if I'm willing to pay more than $5, I'll buy the biscuit packet and then I have to pay $5. I don't have to pay more just because I'm willing to pay more for the biscuits. And this is how the allocation payments are determined. The miner revenue, what EIP does is it burns everything, and the miner in particular gets no revenue. Right. So starting with the seminal work of Roughgarden in 2020, he argues that EIP 559 is the gold standard in the following sense. He argues that this really simplifies bidding for users in the following ways. It is incentive compatible for users in the sense users don't have to be strategic in the way they participate in this mechanism. They, as long as they're willing to pay P, they just go and then just bid whatever their value for inclusion is, and then they'll get included. Right? Just giving, guaranteeing incentive compatibility for users is not enough, because look, users are going to think that they're going to participate in a particular auction, but the miner can alter what outcome is being realized on chain by, out of nowhere just fabricating bids or censoring bids, right? So what Tim argues in his book is that this EIP 559 is also incentive compatible for miners, in the sense that miners don't want to fabricate or censor bids. Okay, so the first two says, tells users like you don't have to worry about being strategic, and the second says you don't have to worry about the miner being strategic. The third says, you don't have to go out of the way to go and collude with the miner and then jointly vary bids so that you get better utility in the equilibrium. Right. So in the following three ways, Tim argues that EIP 559 is the gold standard for transaction fee mechanisms. Right. But our counterpoint is the following. So what game theory and a long literature in economics tells us is that if the miner is basically the monopolist here, it's the only way through which users can touch the blockchain. It feels odd to believe that the miner ends up getting zero revenue in equilibrium, and then the miner is actually content having that, right? So at least from what like all the literature in microeconomics teaches us is that the miner will end up doing something sneaky, so that like they end up generating a lot more revenue than what Tim's analysis predicts. And the mechanism through which we believe this could happen is through off-chain play. So in particular, what we think that the miner will do is it will just go on Twitter and then say, look, I know that the base fee on chain is going to be P. I don't care about it. You have to send me E dollars off chain, and if you're not paying me E dollars off chain, I'm not going to let you onto the block. So what this basically does is, from the user's perspective, even though once again the base fee is P, this just changes the price, right? So if I'm a user, I have to pay P on chain, E off chain, so I have to pay a total of E plus P. So I'm going to behave as if it's a posted price mechanism, but with a modified price of E plus P instead of a price of P. So now the question becomes, okay, what is the price that the miner will want to announce on Twitter? What is the price E that the miner will want to announce on Twitter? So here, from the miner's perspective, the miner can't really predict what each user's individual values are going to be, but we can assume that the miner is a monopolist who has some belief on the distributions from which the values are going to be drawn from. Call this distribution T. So what the miner will do is the miner will pick tau, which is going to be like the total payment that the users have to pay, out of which E is going to come to the miner. So if a user ends up paying tau, what is the revenue that the miner is going to get? The total payment made by the user is tau, out of which P is going to go to the blockchain, like P is going to get burned. So conditioned on including a user, the miner is going to get a revenue of tau minus P. And when will the miner be able to include a user? The miner will be able to do that whenever the user's value is more than tau, the modified price. So the probability with which a user is allocated is going to be the probability that the value V is greater than tau. So the miner's total revenue is tau minus P times this probability. And the miner picks tau so as to maximize the revenue that it gets from every individual user. Right, and it is also straightforward to see that because it is a posted price mechanism, how you allocate one user does not really change the revenue that you get from the a different user. So the miner just optimizes this from a single user perspective, and this is what the miner's optimal off-chain play is going to look like. So the goal for this talk is the following, right? So here we argued maximizing this equation here on this, or this expression here on this slide, is how the miner is going to deviate off-chain in case of EIP 1559. So our talk is for any transaction fee mechanism, we'll try to compute the optimal off-chain play for the miner. And specifically from here on, the question becomes, can we design a transaction fee mechanism such that there is the optimal off-chain play for the miner is to do nothing. Like whatever happens on chain is actually the miner's optimal off-chain play. We call this property off-chain influence proof. Right. So this is probably a good place to pause for a minute and then ask if there are any questions from so far.
Do we know if miners actually do this in practice?
It's kind of yes and no. Because transaction fees are like much smaller in magnitude than MEV and so on. I don't think anybody really cares about transaction fee as of today, right? But this is what is happening with PBS, right? With proportional builder separation, with all the MEV stuff. So one way to think of it is like, even if you don't have MEV, even if you don't have proposal builder separation and all of it to handle MEV, like we should be worried about off-chain play even with just vanilla transaction fee mechanisms. And it's just going to get compounded much, much more because of MEV. Is that good, Avi?
Yeah. All
All
good.
right. All right. Oh, sorry, I didn't get who asked the question. I thought it was Avi. My bad if it was somebody.
Okay.
All right. Let's go ahead. Right. So this off-chain play. So one way to think about it could be, okay, nice. Tim proposed 3 amazing desiderata for EIP 1559. Do we just want to throw this in as a 4th desiderata and then say, okay, along with the other 3, we'll try to find auctions that also satisfy off-chain influence proofness and then try to design mechanisms with 4 desiderata, right? I think it's slightly more nuanced than just missing a desiderata. In particular, I think it's also a consequence of us trying to micromanage every aspect of what's happening on chain, right? Or specifically, the shortcoming is the following. Look, as I mentioned before, the only way through which users can access the transaction fee mechanism is through the miner. And this also means that the blockchain and the transaction fee mechanism cannot see how users and the miners are going to interact off-chain. So are we getting a little too ambitious in saying, okay, I want to exactly micromanage how users and miners are going to interact, even though I have no clue how this is going to happen, right? So to make this point, like to double down on this point a little bit more, I'm going to go on a conceptual rant here. I'm going to talk about designing protocols versus designing mechanisms. So first I'll start by what I mean by designing protocols, and we'll look at consensus as one example for this. So when I say protocols, think of it as free range parenting the blockchain community, right? So this is like, I just set a bunch of loose constraints, and subject to these constraints, I really don't care how agents behave here. Like, it's up to them to figure out how they want to play. So one example here is how we might want to think of today's longest chain consensus in Bitcoin. So what do I mean by constraints? So one constraint can be cryptographic in nature, right? So in Bitcoin, there is non-manipulable leader election. The only way through which you can be elected to propose the next block is if you brute force the hash puzzle, and then in order to extend some block, right? So this is one constraint. The other constraints can be in terms of incentives, right? So the only way in which you can earn block rewards is if you push a block onto the eventual longest chain. You're totally free to mine on top of the genesis block if you want, just that you just won't get block rewards. You are never going to catch up to the longest chain if you start mining on the genesis block. Right? And once we have these constraints in place, like while we kind of ask people to extend the longest chain and not to sit on a block upon mining them, we ask people to broadcast the blocks as soon as they mine them. The incentives are not aligned for miners to always mine on the longest chain or immediately announce blocks, right? So this is the starting point for the entire selfish mining literature, beginning with Yale and Seiler in 2013. So they argue, because longest chain consensus is designed as a protocol, um, there are times when miners would want to try to fork a chain and not always extend the longest chain, and delay broadcast of their mined block even after they mine them. So in particular, the way we should probably think of consensus is as a mechanism and not as a protocol, because ideally, I don't know if we can get longest chain to work this way, but ideally what we would want is, we want people to extend the longest chain at all times, right? Or if you want to do Byzantine fault tolerance, like we want people to sign like very particular blocks. We don't want to give a lot of leeway on how people participate in the consensus protocol. On the other hand, I do believe that we can give people quite a lot of leeway when it comes to participating in transaction fee mechanisms, right? So when I talk about mechanisms, think of it as helicopter parenting. Like we want to make sure everything that is happening on chain happens as we require it to. So the traditional view thinks of transaction fee mechanisms, thinks of it as mechanisms. This starts with, of course, Rafkadin's work and Chang'enchi, and like a long line of work following it. So the traditional view looks at transaction fee mechanisms as a collection of three components. The first is the allocation rule that says, okay, given a set of bids, with what probability do I want to allocate users, right? And then the second is the payment rule, which says, okay, given a set of bids, how much payment should I charge to the three users? And finally, we have the burn rule, which says, okay, given a set of bids or given an allocation, how much of the payments that we collect from the users are to be burnt, and whatever is not burnt is passed on to the miner as revenue. And as I had briefly mentioned in the previous slides, Tim's work argues like, okay, look, the equilibrium on the of transaction fee mechanisms should satisfy simplicity for users in the following ways. So one says, look, you don't have to worry, about how to shade your bid, how to bid, should you bid twice your bid, and things of that kind. If you think your value is V, just go ahead and bid V. Don't try to be strategic. And the second is, look, the auction that you think that you are participating should be the auction in which you are participating. So the miner would not want to change the way the auction's happening by fabricating or censoring bids. And finally, it should be the case that users and miners don't want to collude. And as I mentioned before, it is hard to micromanage all of these components if you don't even know like what is the way through which miners and users are going to collude, right? If you don't know whether the miner can actually tell a user just reveal your value truthfully to me. I'll make sure I'll behave so that I jointly optimize the coalition's utility, right? Or maybe the miner is actually able to commit to that kind of a behavior using TEs or whatever, right? So it is not clear how the interactions between users and miners are going to be. So maybe we just can not worry about it and then say, okay, look, it is between you guys, and then you take it on as you please, right? So the counter proposal to this is maybe study transaction fees as protocols where we just set a loose set of constraints, and then we play the and then we ask whether the equilibrium that these constraints induce are favorable, rather than trying to micromanage all aspects of what happens on chain. All right. So this concludes like the conceptual part of this talk. So from here on, we'll start doing math. So I'll give a couple of takeaways for what I've discussed so far. So the first is this lens of the mechanisms versus designing protocols. So sometimes it makes sense to micromanage the smallest of details, and sometimes it just makes sense to set loose constraints. I don't think we have a good enough narrative yet as to exactly tell people like, okay, this is when you have to micromanage things, and this is when you can set loose constraints. But it would be nice to keep in mind that there are two ways to design things for a decentralized network, right? And the other is much more technical, or specifically for EIP 1559. What happens if you look at EIP 1559 as a transaction fee protocol rather than as a transaction fee mechanism? We saw that the miner will want to go off chain and then choose a price tau that maximizes a very specific equation. Or even more generally, the miner will want to have a non-trivial off chain play. So this is going to be the takeaway for the entire talk. For the rest of the talk, we'll just double down on the second takeaway, and then we'll ask, okay, instead of EIP 59, if I just have an arbitrary transaction fee protocol, what is the equilibrium that will be induced by this protocol? All right. Any questions thus far?
No questions yet.
All right. Great. So now let's go and try to formalize the notion of transaction fee protocols. So as I had mentioned before, so the job of a protocol is to set loose constraints on the agents, right? So we'll try to figure out what exactly the constraint is. As mentioned before, the point here is that payments can't be a constraint because, sure, you can charge payments on chain, but at the end of the day, the miner might just go off chain and then collect payments from the users off chain. So we would give up on payments being a constraint. And instead, what we will do is we'll say, okay, look, the only way through which we can create value to the users is through allocation, right? And the only way through which we can actually make sure there is some value lost from from miners and from the users is through the burn. So we'll make sure we talk about our constraints in terms of the allocation and the burn. So the constraint is going to be the following. So I'll say, okay, if you want to induce, I'll tell this to the miner, if you want to induce an allocation X to the users, you'll have to burn B on chain. There is no other way for which you can induce an allocation X. In this language, EIP 1559 is the following, right? So if the on-chain allocation induced must be 10000, which means one user is allocated with probability 1, everybody else is allocated with probability 0, then the miner will have to burn P. Similarly, if we want 2 users to be allocated with probability 1 and then everybody else have to be allocated with probability 0, then the miner will have to burn 2P and so on, right? Or more generally, beyond EIP 1559, this is kind of like posting a menu to the miner, and then we just say, okay, if you want to induce the allocation X theta, you'll have to burn B theta. And you are free to choose any theta from this menu of options that I gave you. All right. So another way to think of the burn is like there is an artificially imposed production cost on the miner, right? Maybe actually building the block is cheap, but we are just saying, oh, if you want to build this block, this is kind of like your production cost. You have to pay the burn B theta if you want to build the block X theta. So phrasing it this way, reduces this problem to revenue maximization with production costs. And the reason I want to phrase it this way is because revenue maximization with production costs is well understood in mechanism design literature. So we can use tools from much more standard mechanism design literature. Right.
Can I ask a question?
Yes, go for it.
Is the cost only a function of the number of people included, or it can be a function of X?
Right, so it can be about like a lot more intricate details about X, right? So for example, if the allocation rule is like, it can be like, okay, if you want to allocate user 1 with probability 3/4, and if you want to allocate user 2 with probability half, maybe your burn is $5. And if you want to allocate user 1 with probability 1 and user 2 with probability 1/10, then your burn is $6. Right, so it can like depend on the exact allocation that you're trying to induce on chain.
It's a general. It can be a general function.
Yes, it can be general. On the other hand, it can't depend on the values because the TFM does not know the values of the users at this point, right? The TFM is just talking to the miner and then says, okay, just pick an allocation. Is that good?
Yeah.
All right.
Well, Aadityan, you're saying this in the most general manner, like irrespective of collusion proofness.
Yes. So right now I'm just saying, okay, if this is the constraint that you're imposing on chain, what we believe should come off chain. So collusion proofness will impose like one more constraint on top of this later on.
Okay.
All right. Okay. So in order to do this, I'll start with an intro to revenue maximization, like particularly going over Meyerson's seminal work from 1983. So the setting is going to be similar to TFMs. Like we have n users, and these users have values v1 through vn for getting allocated. And we'll assume that these values are drawn IID from some distribution T. We'll assume that this distribution is regular for the mechanism design audience in the talk. But you don't have to worry about what regularity means. It's just like a technical condition that simplifies life for us. We'll assume that this distribution T has a CDF F, a capital F, and a PDF of small f. So now what we'll assume is that the auction can have does not necessarily require users to bid their values truthfully, but there is going to be some equilibrium that is induced in this auction. So there is going to be like some bidding strategy with B, which says, okay, if my value is V1, I would bid B of V1. And if my value is V2, I would bid B of V2. So it just maps my value to what my optimal bid is going to be. And in the equilibrium, I can start talking about the equilibrium in terms of my values, right? So I can say, if I have a value 5, I would bid B of 5. And what is the allocation that I'm inducing when I am bidding B of 5, right? So the allocation X of V is the equilibrium allocation of when I realize values V, or when the users realize value V. And similarly, when users realize a value V and then they bid according to their optimal strategy B of V, what is the payments that we are going to charge from these users? That is denoted by P of V. And finally, the production cost, it's going to be a function of the allocation. So the production cost technically is like, okay, if the auctioneer wants to induce an allocation X, what is the production cost B of X that is incurred on the auctioneer? However, like here we can start talking of X as X of V, right? So we know that when the users have value V, we know what is the equilibrium allocation that they are going to induce. And for this equilibrium allocation, what is the production cost that is going to be incurred on the auctioneer? So technically the production cost should be B of X, but because X is also a function of V here, we can start talking about the production cost as B of X of V. So this is the setting. So here, the goal is to maximize revenue, right? Like that is the auctioneer's perspective here, and in the transaction fee world, that is going to be the miner's perspective. The miner cares about its revenue. However, optimizing for revenue is hard because of two reasons, right? So the first is the revenue sums over all payments made by the users minus the production costs. And it is really hard to talk about what is the payments I'm going to charge in equilibrium from the users, right? I have to figure out what their equilibrium bidding strategy is, and for a given bidding strategy, I have to figure out how other people are going to bid, and is this the payment that's going to happen when people have values V, right? it is a really, really hard condition to verify. And on top of that, it is not just a matter of, okay, now that you have values v, what are your payments, right? If I'm allocating somebody with probability 1 when their value is 10, and then I'm charging them $5, that probably also restricts me, what is the payment that I can charge from people when their value is $11, right? Like I can't allocate somebody with probability 1 and then charge them $3 when their value is $11, when their value is 11, because otherwise, in the world where their value is 10, they might want to deviate and then bid 11 and then try to game the auction. So in some sense, the payments that I'm charging from users is a much more global constraint where I have to figure out, okay, if their value is this, I have to charge this. If their value is something else, I can't charge anything arbitrary because I don't want people to be changing their bids in different cases, right? So optimizing for revenue is much hard, is like really difficult. On the other hand, optimizing for welfare is straightforward. The welfare is just going to ask what is the value that I'm creating in the society. So it asks, okay, what is the value I'm creating for users, which is value times the probability with which they're going to get allocated. However, this is not the total value I'm creating because the auctioneer is losing the production cost. So I look at the total value created minus the total value lost in production cost. And I want to optimize for welfare. So one of the beautiful results from Myersen's work from Myerson 1983 is that if you want to optimize for welfare, it turns out you don't have to really worry about people's incentives. So you take a game theoretic problem and then you ask, I'll get rid of the game theory for now, and then I'll just algorithmically optimize this objective here. And algorithmically optimizing this objective is quite straightforward, right? Like it's just saying, oh, if when people have values v, literally amongst all the allocations that I can play with, what optimizes the total welfare? And then I just solve this as an algorithmic problem, and then I optimize this, right? So if I optimize this problem algorithmically, Myerson comes up with a really nice recipe that I can slap on top of this algorithmic optimal that automatically takes care of the incentives for people. So there exists a way to come up with payments so that optimizing for welfare in the algorithmic sense also optimizes for welfare in the mechanism sense. Okay. So optimizing for welfare is fairly straightforward, and we argued that optimizing for payments is actually hard. And the next part of Myerson's magic is that they argue optimizing for revenue, they find a way to reduce it to welfare optimization. So what they do is that they show the existence of a virtual value function. And this virtual value function is also not abstract. It has like a very nice closed form expression. And what they do is like instead of we pretending that instead of the users having value v, if we pretend that users have a value of phi of v, like modify the values of users according to this function, and then we algorithmically optimize for virtual surplus or the virtual welfare instead of the actual welfare. So there exists the same recipe of slapping on payments on top of the welfare optimization problem. And once you slap on payments on top of this virtual welfare optimization problem, optimizing for the virtual welfare automatically optimizes for the virtual revenue, right? So it takes this really hard virtual revenue maximization problem, and then it says, it just breaks it down into a much more algorithmic virtual welfare optimization problem. And then it gives a recipe to slap on payments on top so that the incentives are taken care of entirely separately to optimizing for revenue, right? Is this good? If the revenue maximization slide is good, we'll get into the details of like our proofs.
Aadityan, like isn't what you just said kind of implicitly assuming that the burn function is symmetric, because otherwise it's not exactly the same as what Myerson did, right? Like you can imagine a world where you burn more for higher value users, right? Like over a cutoff, I burn more, right? Then optimizing for welfare and optimizing for revenue may not necessarily be the same.
Right, so no, we are not literally optimizing for welfare, right? So we are going to pretend that users have a value phi of v1 instead of value v1. And then we are going to optimize for virtual welfare.
So same argument still applies, right? Like it seems like you're making some kind of implicit assumption on the burn. We can talk about it later.
Right. Oh, okay, maybe this might help, right? So the way to think about this off-chain play is not the same lens in which you think about the miner throwing in a fake bid. When we talk about the miner throwing in a fake bid on chain, right, like incentive compatibility for miners, it's a sense of, oh, users bid truthfully, and out of nowhere the miner says, got you, I'll throw in a fake bid of 5 and then increase my revenue. The off-chain play, the way I would think about this is the miner sends on Twitter, look, if you bid this, this is exactly how I'm going to behave. So the miner basically massages the on-chain mechanism into something else. But at the end of the day, the miner still plays out a proper equilibrium. It just runs a different mechanism rather than, doing a got you on the users, right?
Okay.
Right. So when the so when the realized outcome is actually in equilibrium, right? So here we do allow for the fact, or at least on this slide, we do allow for the fact that the mechanism can be asymmetric, because if you have a really high value or a user with a really high virtual value, if you allocate that user, you get if you allocate that user with probability 1, you get like a much higher virtual welfare out of it.
Yeah, like the point is, like when I said non-symmetric, I meant literally you take their indices. Like the first user, I always burn that, this and that, right? Like irrespective of something. That kind of changes the game. But never mind, it's not really fun.
Oh, right. Oh, okay. So the other thing might also be like the burn is not indexed, right? So the burn just says if you want to get this allocation, it does not matter what the values of the users are, but if you want to get a particular allocation, this is the total burn that you have to play. It is not like burn per user also.
Oh, okay, because X is a vector.
Yeah.
Well, you collapse it. Okay.
All right. So we'll get into our first result. So the first result we say is in equilibrium, the off-chain play of the miner will be very identical to a multi-item single buyer setting with the values phi of v1 for the first item, phi of v2 for the second item, and so on. Right. We'll unpack this theorem bit by bit. So the first step of unpacking this theorem is by setting up the multi-item single buyer setting. Right. So the multi-item single buyer setting is going to be the following. So think of it like there are n items, like there is an apple, there's a banana, there's like a bunch of fruits. And then you are like a buyer who's going into a grocery store to buy these n items. So you have values for these n items. So you have value v1 for the first item, v2 for the second item, and so on. And if you buy the first item and the third item, your value is going to be v1 plus v3. Or basically, it's like your value for an item times the probability with which you're going to get that item. And then you sum over, your values are additive over all the items. So as a buyer, what do you see when you go into a grocery store? You're going to see a menu of allocations, right? So you're going to say, okay, if you want to buy item 1 with probability half and item 2 with probability 3/4, this is the payment that the store is going to charge you. If you want to buy item 1 with probability 1 and item 2 with probability 1, this is going to be the payment that the store is going to charge you. So the buyer's decision problem can be written down as a menu of allocations and payments. So if you want to buy items according to the allocation probability x theta, you have to pay b theta. And given this, the buyer picks x theta comma b theta so as to maximize its total utility. So the utility is going to be the value that it gets, which is the sum over all items, the value for the items times the probability with which you're going to get that item, minus the payments that are charged to that buyer. Right. So this is the more traditional multi-item single buyer setting. So we'll reduce the TFM world into this multi-item single buyer setting. So in the TFM world, what does the miner see? The miner sees n users, and then there is this one miner. And if you remember the expression that I had written down in the previous slide, right? The miner is going to think of these users in terms of the virtual value that it gets from these users, right? So if it pushes user v1 into the block, the miner is going to get a virtual value of phi of v1. If it pushes user 2 into the block, the miner is going to get a virtual value of phi of v2, and so on. And as I had mentioned in the protocol lens of a transaction fee mechanism, what does the miner see? The miner basically sees a menu of allocation and burns. So if the miner wants to allocate users according to the allocation probabilities x theta, the miner will have to burn b theta, right? So given this menu, how will the miner play? The miner is going to pick x theta comma b theta from his menu so as to maximize its virtual welfare, right? So the miner will pick x theta comma b theta so as to optimize phi of vi times the allocation probability of user I minus the overall burn that is charged to the miner, right? So what this means is basically if we pretend that the miner has values phi of v1, phi of v2, all the way through phi of vn for allocating the end users, then somehow the transaction fee mechanism world or the off-chain play with transaction fee mechanisms reduces to as if there is just a one buyer trying to buy users or buy items from a grocery store. Is this good? All right. So we'll go over an example. So we look at EIP 1559 and then see if this is similar to what we did before, right? So the menu description of EIP 1559 is as follows. If you want to allocate only one user, you have to burn P. If you want to allocate two users, you have to burn 2P and so on. So as we mentioned before, the miner's choice on an infinite block is basically posting some price tau. And then it gets a revenue of tau minus P if a particular user is included. So this is basically the expression that I had written in the previous slide. The miner gets a revenue of tau from a particular user, while P is the burn that is charged to the user to the miner for including a particular user. However, if I want to optimize for revenue in this form, the way I would have to do this is I would have to differentiate this with respect to tau and then ask, write down a first order condition and then say for what value of tau is this expression maximized. If I write this in terms of virtual values, it turns out that the optimization is like much more simpler. So if I'm a miner and then if I think of this in terms of virtual values, the way I would see this is the following, right? If I include a user, so that is where this indicator comes from, that the user's value is more than tau. If I include a user, I'll have to pay a burn of P for that particular user, right? It need not be as separable amongst users. The burn need not be as separable amongst users for general mechanisms, but at least for EIP 1559, this is good. Like the burn separates out as like a per user burn. And what am I getting back in return? I'm getting phi of vi for that particular user, right? So if I want to make a positive virtual profit out of this user, when would I want to allocate this user? I would allocate this user whenever phi of vi is more than the cost that is incurred. When phi of vi is more than P. In other words, like the threshold that I set, right, should satisfy phi of t is equal to P. That is when, for all values more than t, phi of vi is going to be more than phi of t, which is going to be exactly P. Or more generally, the threshold tau that I choose must actually be the phi inverse of P. An economic intuition here is that I have to include user I whenever the virtual value that I get from this user I is more than the production cost that is incurred on me by the on-chain part of the transaction fee mechanism. All right. So this is a nice way to think about off-chain play. And we look at like a nice consequence that comes of characterizing off-chain play as a multi-item single buyer setting, right? So the exact formula of characterizing the allocation rule and the burn rule in equilibrium is not important. But the theorem here states, as soon as you give me an allocation rule x, I will be able to find a concave function u such that the gradient of that function is the allocation rule x, and the some function of the virtual values, and the gradient of that function is the burn that is going to be incurred on the miner in equilibrium, right? And the reason that this holds basically follows from the multi-item single buyer setting. So there is like a very seminal work due to Roche from 1985 that says as soon as you give me an allocation rule x for the multi-item single buyer setting, you can find a concave function u such that the gradient of this function is the allocation rule, and some function of the gradient of this function u is the induced payment rule onto the multi-item single buyer in that environment. Right. So while I'm not going to use this exact formula for the burn in the coming slides, the takeaway from this slide would be like, from the reduction from the previous slides, we can like straight away characterize what the off-chain equilibrium is going to look like for any given allocation rule X. All right. So for the next part of the talk, we'll move back to the mechanism view of transaction fee mechanisms, going back to Tim's work. But before that, maybe I'll pause for another 30 seconds to see if there are any questions.
No.
All right, sounds good. Okay, so I have 8 minutes. So I'll keep going until I run out of time. So feel free to just tell me when I run out of time. Like I think there are multiple stopping points where we can have. Right. So for the remaining time, let's go back to the mechanism view of transaction fee mechanisms. So we'll go back to the desiderata view, starting with Tim's work. So the first desiderata is on-chain user simple. As I had mentioned before, this just says, look, the user should just bid truthfully on chain. They shouldn't worry about, should they halve their value or should they bid twice their value and so on. The second says, yes, like once again, the auction that the users think that they're bidding must be the auction that they're actually bidding on. So in particular, the miner should not be able to just look at people's bids and then say, oh, if I throw in a fake bid now, all of a sudden I'm just able to increase my bid if I were to behave honestly. And finally, it should also be the case that you don't go off chain and then you try to collude with the miners. Right? And on top of this, we throw back off-chain influence proofness as the fourth desiderata, now that we are going back to the mechanism view of things. And this says, look, the miner should not go off-chain and then massage the mechanism to run their own off-chain mechanism. Right? So specifically, the difference between collusion proofness and off-chain influence proofness is the following. In collusion proofness, the miner and the users just stop being strategic with each other. They just merge into a single entity. And now that they are a single entity, they just say, okay, look, I'll tell the miner what my value is truthfully, and I believe that the miner will behave in the best interest of the users and the miner, the joint coalition. Right? In off-chain influence proofness, the miner goes off-chain, and then it's still playing a game with the users, right? So if the miner says something like, if your value is less than 5, tell me that your value is less than 5, I'll include you for free. But if your value is more than 5, tell me that your value is more than 5, in which case I'll charge you $5, right? If this improves the joint utility of the coalition, that breaks strong collusion proofness. But that might not break off-chain influence proofness, because if this is the option that the miner gives to the users, right? If a user has value 7, if it tells the miner that my value is more than 5, the user knows that it's going to be charged $5. Rather, the user would be strategic with the miner and then say its value is less than 5 and then try to get included, but without paying anything, because the deal was if the user's value is less than 5, the miner lets the user back in for free. So the difference between off-chain influence proofness and collusion proofness is that there is still off-chain play happening, but the people remain to be strategic with each other. All right. So one result that we have from the first of the two papers is the following, right? So we show that no prior independent transaction fee mechanism can satisfy all 4 of these desiderata at the same time. Or specifically, if I start by saying, you have to satisfy on-chain user simplicity and on-chain miner simplicity, then you might have to choose between off-chain influence proofness or strong collusion proofness. And this holds even if I allow you to use some lightweight cryptography, like if we actually use some commit reveal protocols. The proof is a 2-line sketch. Like I won't go into the details, but I'll just give a 2-line sketch. The first step is by now a very standard argument in mechanism in TFM literature, thanks to Chung and Shi, 2023. So they argue, like, if you want a mechanism to be on-chain user simple and on-chain miner simple, that is like, you want users to bid truthfully and the miner to do not to do like sneaky things. And if you want strong collusion proofness on top of all of this, it should necessarily mean that the miner gets zero revenue, right? So this is like very similar to the argument from Chang and Chi. Like I won't go into the details of this argument though. And the second step just says, okay, look, if the miner is getting zero revenue, despite being the monopolist on the current block, there should be some way for the miner to go off chain and then say, you better pay me $5 off chain or I'm not going to let you in, right? This is kind of the intuitive sketch of what the proof here is. So different ways to phrase this is, if we start with on-chain user simplicity and miner simplicity as given, and then I tell you have to choose between off-chain influence proofness and strong collusion proofness. It is not clear when you will want to go with strong collusion proofness, or what conditions or what beliefs you need to have about your blockchain ecosystem that you would actually choose strong collusion proofness, and under what conditions you actually think that you are not that worried that users would collude with the miner and you would go with off-chain influence proofness. So if you want to choose strong collusion proofness, like that is like really well studied. So Chang, Rafgarden, and Shi have a paper in 2024, and Gaffney and Aviv, Yotam and Aviv. I actually started writing down all the years in which they published papers on SCP, but midway I just gave up. They had written like so many papers on SCP. Like they have really nailed down SCP. But on the other hand, on-chain simplicity, like on-chain user simplicity, on-chain miner simplicity, along with off-chain influence proofness, is not well studied. So the goal of our paper is to characterize what happens if we want to go with these three properties instead. So I have 1 minute. So maybe I'll phrase this theorem and then I'll go to the conclusion slide. So what we argue, at least in the deterministic setting, is that the only anonymous transaction fee mechanism, that is, if the transaction fee mechanism cannot discriminate between users, and if it is deterministic, and it has to satisfy on-chain user simplicity, miner simplicity, and off-chain influence proofness, it has to be a posted price mechanism if you don't have access to cryptography. And in particular, note that if you impose deterministic determinism, a posted price mechanism would need an infinite block because anybody who's willing to pay the price P will have to be included on the block. Let me skip the proof and then I'll jump to the conclusion slide. Right. So this is like a summary of the other results that we have in our paper. So first we ask, whether you can have cryptography. If the answer is yes, so it turns out like a second price auction with a specifically chosen reserve in the presence of cryptography satisfies all the three properties that we want: on-chain simplicity and off-chain influence proofness. So if the answer is no, if you don't have cryptography, and if the transaction fee mechanism does not have access to this distribution T, then it turns out you just can't design a mechanism that satisfies all of these three properties. However, if I give access to the if I just tell the transaction fee mechanism like what the distribution from which users' values are going to be, then the next question is the block infinite? If the answer is yes, then posted price is the only deterministic mechanism that satisfies all three. In the paper, we also give a bunch of other randomized mechanisms that satisfies a lot of these properties. And the next question is the support of this distribution bounded? Like, can users have like a value of $1 million to get to be included in this block? If the answer is no, if user is going to have a value strictly less than like some upper threshold, then we show that there exists a randomized auction that satisfies all of the following desiderata, even for a finite block. And if the distribution is not bounded, then it is not it is still open whether you can design randomized mechanism satisfying all three properties for a finite block, right? So this is a run through of the results. I'll finish with the summary. So one is the conceptual takeaway of look, you don't always have to try and micromanage every outcome that might happen on the chain. Sometimes you just try to design protocols, as in the TFM case, and sometimes you have to design mechanisms and make sure you really engineer the smallest of details on chain. And the second takeaway is probably the reduction from transaction fee mechanisms to revenue maximization with production costs and the multi-item single buyer setting. So the way I would phrase this is that all the transaction fee mechanism does is to pose some kind of a constraint on the miner for what block they can build and what corresponding burn that they'll have to make in order to build a particular block. And for that particular constraints, we were able to exactly characterize what the off-chain play would be. And specifically, if whatever payments we are charging from users and whatever revenue we are giving or we calculate to be the off-chain equilibrium, if that also happens to be the on-chain payments and revenue, right? So, or sorry, let me rephrase that. Like whatever resulting off-chain mechanism is, right? So the way I would think of that is the miner behaves as if they are a monopolist with production costs. So I'll maybe leave you with these two takeaways for the talk, and I'm happy to take questions.